Sure, if I can. Like this, yeah. That's great. Way. Tracking of the code. Place back later. All right, so hopefully it will work here. Here. Okay. Oh. Go up to here. So it has all right. So my name is Jonak Kafle. So I have been teaching this course from fall 2020. Before I come here, I used to teach in UW Milwaukee. I did my PhD in 2010. It's about 12 years ago. And after that, I have been working in different laboratories and teaching chemistry, physics, thermodynamics, different kind of courses. So probably you will find me a little bit hard to hear because of my accent. So a lot of students say, oh, you have a thick accent. So bear me with that. So I will try to write in the board, and all the notes are posted in the canvas. So I will just talk that much, whatever is in the note. So if you don't understand me, you go back and look the note. And if you get confused with anything, you can just email me back. Yeah. So like that. So this is although they call it a general chemistry course, it's a very important course actually. Yeah. So if you really have a good base with this course, I think you will do a great in chemistry in future. I think that way. All right. So first chapter is about significant figures. So I'm going to write it here. Significant figure. So this is about the chemical calculations, significant figures. So why do we need significant figures in chemistry? So first of all, why do we need significant figures concept in chemistry, right? So for example, you go to the laboratory and measure three things. So let's say you measure the mass of an object and you found that the mass of the object is 2.305 gram. All right. So you just measure a mass of one object and you found 2.305 gram. And you measured the another object and you found the mass to be 1.2 gram. Now you measure another object and you found the mass to be, let's say, 1.2368 gram. So you have three kind of balance. So one balance shows 1, 2, 3, 4 digit. Another kind of balance is showing just two digit, and another kind of very expensive balance is showing 1, 2, 3, 4, 5 times 5 digits, right? So now you are adding these mass together in your calculator, and you found that I'm adding this number here. So 8, 6, that is let's say, so 2, maybe I put this here, and 6, 8 here. So this is 6 and 8 here. So 8 and 6, 5 is 11, and 3, 1 is 4, 3, 2, 5 to 7, and 2, 3, 4. So you edit this number and you get the mass like this, right? It makes sense? So look here. So this is showing 1, 2, 3, 4 digit after the decimal. So this measurement is very, very accurate. So very expensive balance. Maybe to buy this balance, maybe you need to spend about $20,000. But this one is just one digit after the decimal. To buy this kind of balance, maybe $10 or $20. Make sense? And this one may cost about just a 3 decimal here. So that may cost maybe $5,000 or something like that, right? So this balance cost very, this balance is very expensive, and it is measuring thing very, very accurately. Make sense? So this is a very accurate measurement, very accurate measurement. And this is the least accurate measurement, least accurate. And this is somewhere in middle, right? Somewhere in middle. So our answer here, when we add this one, we cannot report our answer more accurate than the least accurate measurement. That's the whole idea. Make sense? So this is the least accurate. This is very, very accurate answer. So my answer cannot be more accurate than least accurate measurement. Make sense? So my answer should look like the least accurate measurement. So what I do is, so I just make my answer like this. So after the decimal, I have one digit here. So I just report this as 4.7. So I make my answer just the 1 decimal here. So this is not the answer. This is the answer. So if you write this one in this course, you get 0. But if you write this one, you get 5. Everybody got that? Why we need to know the significant figure is the reason is there. Make sense? Good. So there are some rules. So I am going to talk about those rules here. So the idea is our answer cannot be more accurate than the least accurate measurement. All that's what we need to know. Yeah. How about this one? So let's say. So what kind of things are called the significant figure? So let's write a number. So I write a number here, 0. So I have everything here. So I just go through these examples, yeah, so that everyone can follow these things. So I have one number here, 0, and I have 4 zeros here, 1, 2, 3, 4 zeros, and then I have 3, and 1, 2, 3, and I have 2, 0, 0. So something like this. This is a number, right? So I go to the balance. I put my mass, the thing in the balance, and the balance shows this number. Maybe this is milligram, maybe microgram. I don't know. Yeah. So it's all about the measurement. It's not other number. So let's say if I count the number here, our class is now our class is 101 students. This is not counted toward the significant figure. These are the counting number. Counting number are not counted as significant. Make sense? Significant figure is only for the measurement. Like you measure the how many milliliter volume, how many cubic centimeter is the volume, or what is the length, right? Or what is the mass. So only those things we should for the measurement we should use the significant figure concept, not for the counting. So I have 2 students. 2 doesn't count toward the significant. Make sense? So it's only for the measurement. So suppose I'm saying here I have 101 students, So it has nothing to do with the significant figure here. Make sense? So this is that many gram or that many milliliter or that many miles or that many kilometers. So we are measuring that. And how many significant figures are here? So look here, here is a decimal here. If there is a decimal and the number looks like this, so all these front zeros are not significant. Make sense? So they define this way. Now look, the number here, that's non-zero, and everything other are significant. Make sense? So these are non-significant. So significant figures are 1, 2, 3, 4, 5, 6, 7. So this is a 7 significant figure number. Make sense? So if there is a decimal, all zeros that are in the front, they are called the front zeros. They are not significant. And all zeros, all other zeros are significant. Make sense? So now let's look another kind of number. So I have a scientific notation. I have another number here, which is 1.27 multiplied by 10 to the power 24. So it's basically this number is 1.27 multiplied by 10 to the power 24. 24 zeros behind 1. So this is called coefficient. Coefficient, C-O-E-F-F-I-C-I-E-N-T, coefficient. So this is not the coefficient. Only coefficient is the significant figure. So this is not significant. So I have only 1, 2, 3 significant figures. So this number has 3 significant figures. Have you got that? Easy? So like that. So if somebody write 1.270, 10 to the power 24. So again, this zero is counted toward the significant here. Make sense? If somebody write like that way. Good. Now that's a significant figure. Now let's look another one here. So large number with no decimal. So so I'm in the number 3. So large number with no decimal. Let's say 12,000. So somebody say, I drive my car 12,000 miles, right? That's the measurement. Yeah, we are just talking about the measurement. So I drive my car 12,000 miles. So how many significant figure here? There is no decimal here, right? So if there is no decimal, the trailing zero, they call the trailing zero, or the behind zero. These are not counted toward the significant figure. So only this is 2 significant figure number. Make sense? I'm not saying this is a 12 mile. This is a 12,000 mile. But when we report the significant figure, so only the front numbers are the significant figures. Make sense? So trailing zero. So for example, let's say I have 1, 2, 0, 0, 0. So look here. So there is no decimal. So if there is no decimal, so this is significant, this is significant, this is significant. So these trailing zeros are not significant. So this would be 3 significant figure number. Have you got that? So like that. So that's all about the significant figure. For example, if it was like this, 12.000, it would have everything significant. It would have a decimal here, and all these zeros are significant. 1, 2, 3, 4, 5 significant figure here. But here there is no decimal, so all these zeros would be non-significant. Make sense? Got it? Good. So like that. So now let's look the some rules here. How to add? So rules of adding and subtraction. Rules of adding and subtraction. So how to do the addition and subtraction of significant figures. So this is very important for the laboratory. When you go to the laboratory next week, you will do a measurement of mass, measurement of volume, and then you'll find the density, and you'll need to report the answer in some significant figure rules. Yeah. So this is important. So let's rules of adding and subtraction. So here I have numbers 14.23 gram, and I have 8.14 gram. So I have many mass here, and I have 3.6750 gram, and I have 120.4 gram. So I have something like this. So I measured the 4 masses. in balance, and I need to add this mass now, right? Now what I do is I just put this number in my calculator, and calculator give me the answer, right? So the calculator give me 139.09. So I put all number in calculator, and calculator give me this answer. So 139.09. Now again, look here. So this is that we need to look the least accurate measurement here, right? So this is a very accurate measurement. 1, 2, 3, 4 decimal after digit after the decimal. There are 2 digits. Here are 2 digits after the decimal, and here is only 1 digit after the decimal, right? So this is the least accurate measurement. Make sense? So my answer should look like that. Make sense? Everybody got that? So this is the least accurate measurement because it has only 1 decimal after the only 1 digit after the decimal. So this is the least accurate measurement. Accurate measurement. So my answer must look like the least accurate measurement. So my answer would be either you write 139.0, that's good, or you could just round it 0.9 and bring it here as 139.1 gram. This is also good. This is also good. So we are just talking about the significant figure here rather than which number. Well, 0.1 is good or 0.0 is good. So I'm not doing any rounding it. Make sense? Everybody got that? So this is very important. So you will get one question in first exam, some question in homework, and you will get some question in final. So and then you will get some points in laboratory. So so this is very important. Yeah, looks very simple, but it's very important. Everybody got that? Good. So like this one. Now let's do. That's the addition. So if I have to do the subtraction, let's do the subtraction. Same rule. So when I do the subtraction, let's say I measure a mass or volume as a 4.23 gram, and now I need to subtract another mass is 3.1 gram. So I'm subtracting this one. Now I put this number in calculator, and calculator give me the answer. So 4.23 minus 3.1 would be 1.13 gram. So this is the answer given by calculator. So can I report this answer like this? I can't report like this in this course, but in other course, I mean easily, right? So who cares these things in other course? Nobody. So now this should be this is very accurate measurement. This is the least accurate measurement. So my answer should look like this. Yeah. So I would just take this 3 out from here and make look like this. Just 1 decimal here, 1 digit after the decimal. Everybody got that? Good. Like this. So now let's do rules of multiplication and division. Multiplication and division. While I was doing addition and subtraction, I was just looking how many digits after the decimal, right? So for multiplication and division, they do a little bit different way. So let's do this one. Here is a problem. So let's multiply 41.24 grams. So somebody measured the mass of something and reported the number is 41.24 grams. And then he measured another mass and multiplies mass or volume or whatever, 6.01 gram, or it could be volume, I don't know. So this could be mass or this could be milliliter or something. It's all about the measurement, yeah? And then he divides this by another mass. So let's say, or volume, I don't know, 22.30 gram. Now, first of all, we need to look the number of significant figures. So how many significant figures here? So 1, 2, 3, 4, everything is significant there, right? So all are significant. And since these are not the leading zero, there are no trailing zero. So all numbers are significant here, right? And this is a trailing zero, the behind zero after the decimal, everything is significant, right? So this has 4 significant figure here, 4 significant figure. So this has 1, 2, 3, 4 significant figure here, 4 significant figure here. Here also, this is zero is significant, right? We are just concerned which zeros are not significant. If there is a decimal or something, so like this. So let's say this kind of 0.0020. So if zeros are in the front, they are non-significant. If there is a decimal and there is a number like this, and the number and the behind zero, these only these would be significant, right? And let's say if I have very big number like this and there is no decimal, these are not significant. Only this will be significant. That's the only rule I have, right? Only these two things we need to know. Now this is 4 significant. This is 3 significant figure, and this is 4 significant figure. Now I put all the things in calculator, and calculator give me the answer, and the answer is 11.445. So calculator give me this answer. Now my answer should look like the least number of the significant figure. So look here. So there are 4 significant figure. My answer cannot look like this. I have 4 significant figure. I cannot report my answer in 4 significant figure. I need to look here, which has a least number of the significant figure. Make sense? So this has 1, 2, 3 significant figure. So my answer must look like 3 significant figure. Make sense? So I'm going to make this 3 significant figure. Now I have 1, 2, 3, 4, 5, 6, 7 significant figure here, right? So I should not report the answer like that way. So my answer should be 11.1 gram. So I just report whatever is a gram. Yeah, gram, that would be gram there. So look here. So now I have 1, 2, 3 significant figure here. I have 1, 2, 3 significant figure here. So if there are a multiply and divide, you just look the least number of significant figure in your measurement and report the answer like that way. Yeah, but if you are doing the addition or subtraction, just report as a decimal, which has the least decimal places in your measurement. Everybody got that? Confusing? I don't think it's that confusing, right? So like this one. So now, so I just finished 2 slides. Now I'm going to work in the rounding. So I just talk about a little bit about the rounding, how to round. So probably you already know, but if you don't know, so let's talk a little bit about rules of rounding. So how to round the number. Rules of rounding. So rules of rounding. Rules of rounding. So let's round some of the number. Let's say I have a measurement, or I have a answer like this, 4.234, something like that, right? Now let's say I want to round here. So I just want to, so this is 1, 2, 3, 4 significant figure, right? I want to report this as just a 2 significant figure, meaning that I just want to round thing here, right? So what I do is, if there is a 5, 6, 7, 8, or 9, I just got this number and add +1 in front. So like this. But if there is a 0, 1, 2, 3, or 4, I just got this like that. Yeah. So let's say here is a 3. So this is one of these numbers, 0, 1, 2, 3, 4. So this is one of these numbers. So I just drop this number and my answer is 4.2. Make sense? I'm just trying to make 2 significant figure in my answer, right? Make sense? So let's say I have something like this. So I have 2, 5, 6. So something like this, and I want to round here. So I need to drop this number here. So I just drop this number and add +1 in this front number like that. So that would be 4.3, and other are dropped. So 2 significant figure here. Make sense? So if you are cutting 5, 6, 7, 8, or 9, you just cut those numbers and add 1 to the front number like this, and just report that. But if you are cutting 0, 1, 2, 3, 4, just drop it, and you don't have to add 1 in the front number. Easy? Not that hard, right? So let's. Is there anything here? So let's practice one here. 2.562. I have a number here. 2.562. So 2.562. So 2.562, I need to report answer in two significant figures. So I want to report only up to here, 2.5, right? Now I need to put this number here. This is 6. So this is 5, 6, 7, 8, 9. So one of these numbers. So I'm just going to put this one and going to add plus 1 here, and that would be 2.6, like that, right? Everybody got that? So, but again, rounding is not that important in this course because the answer is already given. So you just need to pick one answer, right? So, but if you want to round this number somewhere here, 2.562. So if you want to round this number here to report in three significant figures. So 1, 2, 3 up to here, right? So if you want to report your answer in three significant figure, you are going to drop this number. Now so you are not putting this one and adding 1 here because this is 0, 1, 2, 3, one of those number, right? So I'm not adding anything here. So I will just write 0.56 like this. Yeah, easy, right? So it's a little bit confusing. So, but should be okay. So there are some problems here in slide number 4. So let's do those problems here. I just pulled this from your book. So they are doing 0.12, 1.9, and 10.925. So these are three numbers. They are adding this one and reporting the answer according to the rule of significant figures. So just plug this number in calculator, and calculator will give you 12.945 gram or milliliter or whatever is the measurement here, right? Now, since we are doing addition here, we just need to report the answer as a least accurate measurement. So there are, this is accurate, this is very, very accurate, this is the least accurate, right? So my answer should look like this. Make sense? So this should be 1 decimal. So what I would do is, that's 12.9. Yeah? Make sense? Good. So there is another question here. So that question is division. So they are doing 0.01208 and they divide by 0.0236. So you just plug this number in calculator. So this is the division. So you divide this number by this number, and calculator will give you 0.51186 like this, or maybe many digits there. So now let's count the significant figure here. So these are the front zeros. These front zeros are not significant, right? So only 1, 2, 3, 4. This is the fourth significant figure number. So this is fourth significant figure here. These are front zeros. So these are not significant. Only this one, and this one are significant. So this is the three significant figure. So I told you, look the least significant figure number, right? So my answer should not look like this. My answer should look like this. Everybody got that? So that is three significant figure. Now 0. So this 0 is not significant. So 0.511. So this is 1, 2, 3 significant figures. So I write 1, 2, 3 significant figure because this is not significant, right? So if you count this as a significant, that would be 4, but this is not significant. Front zeros are not significant. Make sense? Everybody got that? Yeah. So like that. But what I could do is I would just do the rounding here. So if I want to express my answer as three significant figure, I could just drop this 8, and since 8 is one of those number 5, 6, 7, 8, so I would just add 1 here plus 1 here, and I would write 0.512. Yeah, but you really don't have to do something like this. If you write something like this, that's okay. Yeah, 0.511 and 0.512 for me is the same number basically. Everybody got that? So rather than rounding, looking the significant figure and counting the significant figure is important in this course. Yeah. So here is the one problem. So you will be doing in lab 1. So this is from our book. So mass of you have a book and you measure the mass of a book, right? You have a chemistry book. You go to the laboratory and you put in the balance, and the mass of the book is so the mass of the book is 13.56 gram. 13.56 gram. And you measure the length of the book, breadth of the book, and the height of the book. And if you multiply length, breadth, and height, you get a volume of the book, right? So the volume of the book is, you measure the length is 6.45 cm, and breadth is 2.50 cm, and height is 0.31 cm. So you have a book like this, and then you put this one in the balance, and you measure the mass of the book is this much, and you measure the length of the book, you measure the breadth of the book, and you measure the height of the book, this one, and you get this this parameter, right? And you multiply length, breadth, and height, and you get the volume. So when you plug these number in calculator, and the calculator give you 4.99875 cubic centimeter. So one centimeter, another centimeter, another centimeter. So I have 3 centimeters there. So that's that many cubic centimeter, right? Now, again, we are doing the multiplier divide here. Now we need to look the significant figure rule. So we need to make our answer is the least number of significant figure, right? Least number of significant figure. Let's count the significant figure here. 1, 2, 3. This number is 3 significant figure number. This one, so the behind zeros here are all significant in decimal, right? So this is also 1, 2, 3 significant figure. And here, this is the leading zero, the front zero. This is not significant. So I have 1, 2, only 2 significant figure here. So my answer must look like the number that has the least number of significant figure, right? So my answer should look not like this, but it should look like this. Make sense? So like that. So I'm going to do 4.9 cubic centimeter like this. So only 2 significant figures. So I just make these 2. These are 2 significant figures. Make sense? So I could do rounding here. What I could do is I could just drop this number here and add 1 here, and I would do 9, 1, 10, and 5. I could do 5.0 also, but you really don't have to do that one. Yeah. So again, I'm saying the significant figure is important than rounding. So what is the difference between 4.9 and 5.0? Is almost the same, right? So this 4.9 cubic cm, or you can write a 5 cubic centimeter. Either way is fine. So if you write the 5 here, you would write 5.0 because this is 2 significant figure, and this is significant, and this is also significant. You would have 2 significant figure if you have rounded. Make sense? But you really don't have to. Good. Like that. Now I have for a while, let's say I rounded this one here, and I write a 5.0 cubic centimeter. Since I am doing here, or the book is doing the rounding and putting the answer like that. But it's okay up to here. If you do up to here, that's fine. Make sense? Good. Now I have a mass. Now I have a volume. Now we need to calculate the density. So what is the density formula? Density is equals to mass divided by volume. So this is our lab 1. So we will be doing this lab 1 like this. Yeah. Next week. So mass is 13.56 gram. So 13.56 gram here, and then volume is 5.0. You could write 4.9. That's fine. Yeah. Either is fine. So I'm writing 5.0 gram here. Sorry, cubic centimeter. So that's cubic centimeter here, like this. Now, so put this number in calculator, and the calculator would give you 2.738 gram per cubic centimeter, something like this. Yeah. Now I need to report the answer according to significant figure rule here. 2.31 here. So look here. I have 1, 2, 3, 4 significant figure there, but here I have only 1, 2 significant figure, right? This is the division, right? I'm dividing. So my answer should look like the least number of the significant figure number. Make sense? So my answer should not look like this. My answer should look like this. So it has 2 significant figure. Since decimal, the zeros after decimal are significant, right? Small number, zeros after decimal are significant. So 2 significant. So my answer should look like not 1, 2, 3, 4. See, this is 4 significant figure. That's too many. I cannot report like that. So my answer should look like 1, 2 significant figures. So I just write 2.7 gram per cubic centimeter. So this is 2 significant figure. It look like this number. Everybody got that? So like that. Good. Any confusion? So when you go home and you read couple of times and it makes sense, yeah. So we need to repeat many times through problem and we are good. So we really learn a lot of things in this half an hour. Now this is all about the significant figure, and we are done with the significant figure rule and how to do the calculation, how to do rounding, yeah. So now let's go to the next slide and we talk about the scientific notation. So I am now in the 5th slide. That is what's that one? Scientific notation. Scientific is C-I-E-N-T-I-F-I-C. Scientific notation. Scientific notation. So the very small number and very big number are hard to memorize, right? And so we need to have some rule so that it's easy to memorize. Make sense? Or easy to handle. Therefore, we need a scientific notation. For example, if you say somebody the mass of a bacteria is 0.000000321 gram, it's very hard to tell somebody what is the mass of the bacteria, right? It's very hard to handle the number like this, right? So we need to express this number in such a way that it is easy to memorize and talk with other people. Make sense? So I'm just making this number. It's not the mass of the real bacteria. Yeah. So like that. So what we do is we need to express this number in a scientific notation. So scientists don't write the numbers like this. Yeah. So how they do is they do like this. So what they do is they go. So if these are the small number like this, so what they do is they go back and reach a number like this. So they reach here. So from here they reach a number and just go behind that number. Make sense? So now what is this one? 3 point. So they put this decimal right there, just after the first number. Make sense? All are zero. So 3.21, and then they write multiply 10 to the power. So they go back. So if they go back, they need to put minus in top here. And how many steps they go back? So 1, 2, 3, 4, 5, 6, 7 steps. So they go 7 steps back. So they write like this way. Make sense? So the mass of the bacteria is 3.1 10 to the power minus 7 grams. So it is easy to handle and easy to work with. Yeah. So scientific notation. Why we need a scientific notation? It's easy to tell the story, easy to tell other people, or easy to work with. Everybody got that? So like that. So this one. So if you are going back, put minus here. Yeah. But if you are going front, then you need to put the plus sign there. Or you don't have to put anything. If there is nothing, that means that there is plus. Make sense? So let's write another number here. So I have 324. So I have another here. So I'm going to use this number here and write one example here. So I have 324,000 gram of something. So 324,000 gram of something, right? It's very hard to tell somebody, right? Now I need to put this in the scientific notation. So imagine that there is a decimal here. There is a decimal here at the end. If there is nothing, we just imagine. If there is a decimal, that's fine. If there is nothing, we imagine that there is a decimal. Make sense? So let's go front and make one number before the decimal. So I go like this and just one number before the decimal here. Make sense? Everybody got that? So like this. So that is 3. So this decimal, I put it here. If there was decimal, that's fine. If there was no decimal, I just imagine that there is a decimal here. Yeah. And then I put that in such a way that before the decimal, there is only one number. Yeah, so 3.24000 here. So like this, and then I say 10 to the power, sorry, I don't have to write these zeros here. 3.24, 10 to the power 1, 2, 3, 4, 5. So I go the 5-step front here. So I just write 5 here. So 3.24, 10 to the power 5. Make sense? So if the decimal goes forward, just either you can write the plus here, but many of the book don't write plus. Yeah. So just you don't have to write anything there. If there is nothing meaning that there is plus. Everybody got that? So if you are moving backward, we have to put minus sign. If we are moving forward, that decimal, we just don't write anything. That means that's plus. Yeah. Good. So that is one, and I have another here. So that's a big number. I have 2 examples there. Now I'm going to write the small number here and 0.0012. So now express this number in the scientific notation. Now I move this decimal so that one number is before that decimal. Yeah. So I'm going to move this one like this way so that there is a 1 number before that decimal. So I will put decimal here, and this 1 would be before the decimal, right? Everybody got that? So that is, so 1.2. So 1.2. Now multiply 10 to the power. Since I moved the decimal back, so I am going to write minus and 1, 2, 3. So I push decimal 3 step back. So I put minus here because I pushed the decimal 3 step back. Everybody got that? Yeah. Like this. Good. All right. So I think we are good with this mathematics things here. Now we will talk about the accuracy and precision. So is it okay? Are you understanding me, or I'm going too fast? It's okay. All right. So, but again, if you don't understand, if you have any confusion, just email me, and I'm always available to reply the email. Yeah. So let's talk about the slide number 6 here, and we have accuracy and precision. So accuracy and precision. Accuracy and precision. So this is the duster. So let's take the example. This is the duster. Who makes this? This is a company makes this and sells it, right? And the company has specification. They say, oh, this is the duster we make, and the mass of this duster is 10 gram, 10.2 gram. They do the measurement, and they have to send this with the label, and that label comes with some specification, length, breadth, height, and mass, everything, right? So let's say the mass of this duster is, let's say, I just give one example here. So the company make the duster, and we bought that duster here, and the mass of that duster they reported is 10.23 gram. So who report this answer? The company who make this duster report this answer to us. Make sense? Make sense? Because when I buy the duster, there comes the label, and there is some a sheet where there is a length, height, breadth, and mass, everything they have to report. Yeah. Otherwise, they can't sell the product in the market. So, so they reported 10.23 gram. So we need to trust this number, because we don't trust ourselves, because the company make this duster, and they have the multi-billion-dollar industry. They have the very high sophisticated equipment to measure, right? So in our home, we cannot have that accurate measurement, and we don't have a skill to measure length, breadth, height, or mass accurately. So we need to trust their number. Yeah. So this is the very standard number, because we are trusting them, right? So we call this as a true value, or standard value, or company value, standard value. Right. So either this is done by the government people, or the big laboratory, big industry people reported this number to us. Make sense? Now we bring this to our laboratory and we start to measure the mass of this one, right? So one time I measure, so that's the government reported us, or the industry reported us. One time I measured this in our laboratory at UWEC. So we have a chemistry lab. We need to measure the mass of this one in our laboratory. So one time I measured the mass of this guy and I got 11.5 gram. Another time I measured the mass, I got 7.8 gram. Another time I measured the mass and maybe I got 15.6 gram, something like this, right? So look here, am I close to this one? No, right? I'm not close to the standard value. Am I close to each other? One time I got 11, another time I got 7, another time I got 15. So maybe my balance is broken. Yeah, it's not showing the good number. Make sense? So my answer are not close to my answer. This answer is not close to this. This answer is not close to this. So my answer are not close to each other. So I am really working bad. Yeah. So I am not precise. So this is called not precise because I am not being able to find the number close to each other. That's my measurement. Make sense? So I'm not precise. Am I close to the true value? No, I'm not close to true value, right? So I'm not accurate, accurate, like this. Everybody got that? So if I have got something like this, so if I measure the mass, let's say I got one time 10.5, another time 10.4, another time 10.1. If I got something like this, look here, my all number are very close to each other. I'm very precise comparing with myself, right? And my values are very close to the company value, the true value. So I'm very accurate and I'm very precise. Yeah. So it's very hard to be accurate, but we need to try to be very precise. Make sense? So let's say so that the company value is 10.23. So I measure the mass 3 times. So 15 gram one time, another time 15.5 gram, another time let's say 15.4 gram. I'm doing something right here. 3 times I measure and all the time I got the 15, but I'm not being able to get their value, right? But I'm doing very good because 3 times I did it and I get all number very similar, right? I'm very precise. I'm very precise, but I'm not accurate. Maybe the company is reporting something bad, or maybe I'm doing something wrong there, but there is a very tiny difference. Maybe I'm doing some calculation error. Maybe I'm doing something error. So we try to be accurate. We try to be precise rather than accurate. So accuracy is not what we are looking for. We are just trying to be precise as a scientist. Make sense? So if you cannot be precise, it's very hard to be scientist. So we need to be able to reproduce our answer. Make sense? So if I do three experiment and if I get all 3 numbers very close to each other, so even though I'm not accurate, I'm doing very good here. So I can go back and look the data, or I have something error in the balance, I can go back and fix. So this is precision is good. Yeah. So first of all, we need to look at precision, and when we are precise, and only we can go and try to fix things and be accurate. Make sense? So like that. So I have some definition here. Your measured values are close to each other, meaning that you are precise. This is your measured value. This is your measured value. This is your measured value. So your measured values are close to each other. That means we are precise. Make sense? Then accuracy. Your measured values are close to standard value. So if you are measuring duster light and then you are getting this one, and the company also reported that the mass of the duster is 15.0. So if these are your measured values and this is the standard value, your measured values are close to the standard value. That means that you are accurate. Make sense? So precise is I'm comparing with myself, right? My skill, I'm comparing my skill one time, another time, and another time. And if my skills are close to each other, I am precise. Make sense? But for being accurate, I am comparing me with somebody else who is very, very highly placed somewhere. Yeah. Good. So here are some examples. So in next week class, we will do in class, yeah, in the laboratory. So so what we will do in the first lab is we will measure the density of water. So what is the density of water? So people have done this experiment in very big laboratory from many, many years, and they found that the density of water, D is 1.0 gram per cubic centimeter. So this is the standard value of the density of water. Make sense? So meaning that if you take 1 gram of water and measure the volume, you will get 1 cubic centimeter volume of that water. Make sense? Or if you take 1 milliliter or 1 cubic centimeter of volume of water and put in the balance, you will get 1 gram mass. Make sense? So this is the density of water. So this is 1.0 gram per cubic centimeter is the density of water, and we will be measuring in laboratory in the first class, and we will try to find if we get this one or not. Yeah. So this is the true value or standard value. True value. You could say standard value, and then we will be determining the density of water in our laboratory, and we got 1.92 gram in gram per cubic centimeter in one experiment. And I repeated the same experiment, and I got 1.95 gram per cubic centimeter, and then I repeated again, and I got 1.94 gram per cubic centimeter. This is the real experiment we will be doing. Yeah. Look here. My number are very close, 1.92, 1.95, 1.94, right? I'm doing something right. So what could be wrong? Maybe my water is not right. Maybe somebody mixed salt in the water, or maybe something, the water is contaminated, right? Something heavy thing is being dissolved there, like sodium chloride. So something is wrong with the water here. But I'm doing right? I cannot change the water. So I'm very precise because my measurements are very close to each other. So I'm precise. Am I getting the my measurement value equal to the true value? I'm not getting. This is 1.0. I'm almost getting the double, right? Almost 2. 1.94 is almost 2, right? So I'm precise here. This number shows I'm precise here, but my number is not close to the true value. So I'm not accurate and not accurate. Everybody got that? So like this, yeah. So that's how the scientists work, yeah. So maybe you're just starting, so you don't know science is something, very high level thing. I used to think when I was doing masters or even the first year in the PhD student, I always thought that, oh, I cannot do science. The science is something hard. But once you go to the laboratory and start to do the thing, the very limited thing we do in the laboratory, we don't do that many things actually, yeah. So like this. So I am precise. The data are very precise. I'm doing good. My skills are very, very good, but my water is not good. Maybe somebody mixed something in the water. Yeah. Or maybe I'm doing something wrong with the calculation. I don't know. Yeah. So I can easily fix this problem later. So I'm precise, but I'm not accurate. So like this one. Now, let's look another example here. So example 2 I have here. So example 2, the true mass of a dime is 2.268. So dime. So the true mass of a dime, 2.268 grams. So the true mass, who report this 2.26, the dime. So who make the dime? The government makes the dime, right? So and then they say, okay, the mass of one dime must be 2.268 grams. So they post this number in the standard book or in the website, right? Now we bring the this dime in our laboratory and measure 3 times. So most of the time we do the experiment 3 times. Yeah. So when we do the 3 times, we trust the data. Yeah. Now one time I measured the mass of the dime and I found 2.264 gram. Another time I measured it and I got 2.263 gram. And another time I measured the mass and I got 2.268 gram. Look here, my number are very, very good. 2.264, 263, 268. I'm doing very good. My skills are really good. I know how to measure the mass of the dime, right? So I'm very precise. I'm very precise. Now, are my number equal to the standard value reported by government? Look here, 268. So 263, 268, 264, all 26, 26, 26, very close, right? So we are very close to the time. So we are very accurate. So our accuracy, we are very precise within our skill, and we are very good at replicating the government number. So we are very accurate also. Everybody got that? So I will be putting something like this in homework or in exam. Yeah. So you don't have to memorize too many things if you understand these things. Yeah. Good. Yes. Nobody knows actually how close we should be. It depends on situation to situation. So I was working in the battery industry with the Johnson Control and other big laboratories, and they said they would be looking within 10% of the error. So in the battery, maybe 10%, maybe in the medicine. So I was looking this blood sugar meter. So the diabetics use the monitor the blood sugar every day, right? And so I was doing a little bit research with the different sugar measuring those tiny devices, and they were saying plus 10 to minus 10 error, plus 10 to minus. So they were looking, so plus 10 to minus 10. So about within 20% error. Yeah. So it's I think it all depends on how closely people can measure something. Yeah, how closely. So for example, bacterial load probably you cannot measure very accurately, maybe 20% or 50%, right? But big thing, if you are measuring these things, but maybe within 5% error you can measure these things, right? So it just depends what you are measuring, I think. Did I make it clear? So probably this is the big thing, and if I measure this thing, I don't think I make 10% error. Maybe it's about 1% error or 2% error. Most of the time, this density measurement comes very close to 1 in our laboratory. So within 5%, yeah, something like that. So it depends what you are doing, how delicate things are, something like this, yeah. So there is not standard rule. So let's say if you are within 10% of error, that's good. Something like this. So so this is the accuracy and precision. Now not precise. So let's see one example here in slide number 7. I'm in the slide number 7, and there is one example in accuracy and precision. We buy a piece of copper, and the seller or the company says the mass of that piece of copper is 10.0 gram, which is a 10.0 gram. That is the standard value of the mass of a piece of a copper, right? So and I bring in the laboratory and measure 3 times, and I got 7 gram, 7.0 gram. Then I measure 8.0 gram, and then third time I measure, I got a 9.0 gram. So I'm not close to my measurement here. 7 gram, 8 gram, 9 gram is too much a difference, right? So this is a least precise. It's not precise. So let's say it's not precise. My values are not close to each other, not precise, and I'm also not close to the true value. So this is the seller's or the company value, seller's value. So not precise and not accurate. So this situation is not precise, not accurate. And again, I'm saying we are not really looking this one, we are looking this one. So if we are not precise, that's a hopeless situation. We need to try to be precise always in the laboratory, even though we are not close to the true value. Everyone got that? Precision is something we are looking for, yeah? So first year graduate student or first year undergraduate student go to the laboratory in the professor's lab, and they start to do something, and they are measuring one thing, and sometimes they got 15, they got 19, they got 30. So they are everywhere. So they don't know how to use the instrument, yeah, or they don't know how to make the solutions, or they are doing something really bad. They don't have skill, yeah. So that's a least accurate condition. But if somebody is highly skilled working in the laboratory, they don't get something like this, 15, 19, 30. So if he's getting something like this, and he immediately do either the machine is broken, or the chemicals are bad, but something is wrong there. Yeah, everybody got that? Something like this. So we need to try to be precise. Yeah. Good. So there is a diagram here, and sometimes this book present this accuracy and precision in the diagram form. So let's say you go to the some game, and they hit the arrows here. Here is the bullseye, and something like this, right? So if you go to the playing the arrow hitting the bullseye, so if you hit here, you need to hit here, right? So if you hit here all the time, you are accurate, and you're one time you hit here, another 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 time you hit here. So you are very close to each other, and you are hitting where you need to hit. Make sense? So you are accurate and you are precise. You are doing really good. Make sense? So sometimes book present like this way, yeah, rather than the data I presented previously. The book present like this way. So you are accurate and precise. But let's say one time you hit here, another time you hit here, another time you hit here, another time you hit here. That's bad. So now you are neither accurate nor precise. You are one time accurate, but one time accurate is not your skill. So that may be coming from somewhere, yeah. So one time you hit one time accurately, but 4 times you just are everywhere. So that's not your skill, yeah. So this is I would not say this is this condition is not accurate, not precise. Make sense? Now let's say another time you need to hit here to win the prize, but every time you hit, you are hitting here, you are hitting here, here, here. You see that? You hit many times, you need to hit here to get the prize, but you are hitting here. So you have really good skills, yeah, but you just don't know why you are hitting here rather than here, right? So you are if you do a little bit different in your way of doing, you would probably get the prize, yeah, because you are really good at hitting at one point. Make sense? So you are precise, but you are not accurate. You need to hit here, you are hitting here, right? So not accurate. Everybody got that? Easy, right? Right. So if you are hitting where you need to hit all the time, you are accurate and precise. But if you are not hitting where you need to hit, but you are hitting every time at certain point, you are precise but not accurate, right? Then like that, yeah. So you can just look the diagram there in lecture 2. Then that should be good. So high accuracy, low precision, high, yeah. So good. Now, so we really go moving very fast. I used to teach only a 50-minute class previously. So this time we are talking 1 hour and 15 minutes. So it's a long class. So because of the college rule, even if we are done, we cannot leave. We need to stay up to 1 hour and 15 minutes here. Yeah. So now we go to the next slide, and probably I can log into this computer and show you periodic table. So all right, so before showing the periodic table, I just want to show one more math trick here. And so let's say So don't think it's a complicated thing. Something I'm going to write here, you probably have never heard, or maybe you have already heard. So let's say 18 gram of water, 18 gram water is called as 1 mole water, 1 mole water. So probably you don't know, so you really don't have to understand at this point. So 18 gram water is called 1 mole water. Somebody say, oh, give me a 18 gram water. So the common people say 18 gram water or 18 milliliter water, 1 liter water we say, right? But the scientists working in the laboratory may say, oh, give me a 2 mole water or something like this, right? So this is a math trick. So let's say, so it will be an exam, yeah? It will be an exam or in the homework too. So let's say you have 40 gram water. You have 40 gram water, 40 gram water. Now I ask you, convert it into moles. Yeah. So I give you, oh, it's a 40 gram water is there. How many moles of water is there, right? But you don't have to understand what moles means now, right? I'm just trying to show you the math trick. Yeah. So 40 gram water. So what I do is I take 40 gram here. So I'm going to convert 40 gram water into moles. So 40 gram is here. Now I need to convert into mole. So I don't need gram here because he's asking me to convert into moles, right? So I multiply this in such a way that this gram is cancelled. So what I do is I don't need gram, so I put the gram part down here. So this is my conversion factor. So this is a gram here. So I put the 18 gram here, so that if this gram is up, this gram is down, I can cancel these grams. Make sense? So something I don't need, I put that factor in such a way that something I don't need, I can cancel that. Make sense? And then since I need the mole, so I'm going to put this factor up here because I need mole. So that's a 40 divided by 18, and then that would be 2.1 mole or something like that. Make sense? So put the conversion factor in such a way that something you don't need, that you need to cancel. Easy? Good? So still you don't know what moles means, right? Now, but you can do the math. Good? So like that. Everybody got that? Good. So let's do another one. So convert 60 moles of water to gram. 60 moles of water to gram. Water to gram. So let's convert this one. 60 moles of water to gram. I need to convert 60 moles of water to gram. You are already given this this conversion factor. This conversion factor you don't need to remember. You just can print, or it's given in class. So yeah, something like this. So let's convert. So I don't need moles here. So that's a 60 moles. I don't need these moles. I need a gram. So I put this factor in such a way that I don't need this mole. I need to cancel this mole. So I'm going to put mole part down here, 1 mole, and then I need a gram because 60 moles of water to gram. So gram part, I need to put that up here, 18 gram. So mole cancel here, then 16 multiplied by 18, put in calculator, and whatever comes in gram. Everybody got that? Like it. Good. It's very important. So we will be doing a lot of chemical calculation, and frequently we do this kind of conversion. Yeah, good. All right. So that's the math trick I just wanted to tell you. So there are some problems you can look yourself. Now I'm going to show you a periodic table here. If I can log in here, let's see. Yeah, I can do it here. So I am in the chapter 1, lecture 2 slides. So I just want to talk a little bit about the periodic table. And all right, so I'm going to here. The periodic table is like a toolbox. So if you want to work with anything in home, we need a tool, right? So periodic table is a toolbox for chemistry. So I'm going to show you here. I just Google, or maybe I just put my SanDisk here. So I was showing this previously. So some precision. So this is a precision, not accurate. This is low accuracy, low precision. This is also high accuracy, low precision. But this is really a good point. High accuracy, high precision, something like that. So let's talk this one. All right. So probably I cannot show to the online people here, but I I don't know. So this is called the periodic table here. So probably you can look here. So all these orange, you see here, these are blue elements. So these all are blue here. So these are blue, these are blue, these are blue. All these blue elements here are metals. So they conduct electricity and heat. So make a wire of those elements and connect in the your cell phone using those wire to the plug, and the cell phone gets charged, right? So that means the metal. Make sense? So all these blue elements have similar property, and they are called metal. So this is metal, then metal, these all are metal, these are metals here, these are metals, everything is blue. Blue or light blue, every blue things are metals here. And you can see here this green. So this green, this green, this is green, this is green, this is green, this is green. So there are few green elements, 1, 2, 3, 4, 5, 6. So there are 6 green elements. So sometimes in some conditions they show the metallic characteristics, and sometimes they show the non-metallic characteristics. Some of the properties, in some of the properties, they behave like metal. Some of the properties, they behave like non-metal. So we call metalloid. Make sense? So, and then you see here, so there is a hydrogen here, one element here, and there are other orange elements. So this one, this one, this one, this one, all these elements here, which are orange elements, they are non-metal. Make sense? So they don't conduct heat and electricity. Make sense? So there are 3 kinds of element in periodic table: metal, non-metal, and metalloid. Metal conduct heat and electricity. All those blue elements, these green elements sometimes conduct. Sometimes some of the properties they have metal-like. Some of the properties they have non-metal-like. So they are called metalloid. And some of all these orange elements there, they don't show the metallic characteristics. That conductor of heat and electricity, most of the time they are either gas or liquid or something like that. So they are non-metal. Make sense? Yes. How does what word? Oh, the neon gas. That's another. That's not a metallic thing. They call that is a spectroscopy. We need to explain that in the spectroscopy term. So there is a gas and the neon gas, and we need to supply the very high voltage to the gas, and there are some electrons in that gas, and when we supply the high voltage, some of the electrons from lower or mid jump off, and you are supplying the some of the light they release is a neon gas color. Yeah, because that's not a conductor. Yeah, so we are just giving the very high voltage to that gas, so that some of the electrons jump from lower to higher. Yeah, that's different. So like this one, and so almost done here. So yeah, probably. So we are in 12. So maybe we stop here and we continue in next class. Yeah. So hopefully you enjoyed the class. Thank you, everyone.